keynote presentation. Title is Virtual Human from Entertainment to Social Media to Metaverse and Beyond. It sounds like a quote from Buzz Lightyear, but I cannot think of anything more interesting than these three sectors: entertainment, social media, and metaverse, and they all kind of have application for meta-human use. And for me, and thanks introduction from Jonathan, and I'm with these companies or institutes before, and have some kind of film created or video game. As you can see, mostly like in the recent 10 years, like hobbies, Fast and Furious, Avatar, Call of Duty. So I do like to watch movies and play video games, and I see a lot of usage for virtual human in them. So that's why this virtual human have been one of my favorite topics for my entire career. Bear me if you see the video in like a little bit choppy. I think we try our best to set up a system. But this is a movie from about 3 years ago. Gentleman and Man, directed by director Ann Lee, and as this, if you haven't seen it, the story is about like someone clone, being cloned from an assassin, professional assassin. But so his younger version is trying to kill him. And then in this movie, they try to digitize Will Smith, which is the main actor. And a lot of sequence is like for this younger version of Will Smith is truly believable. Like you won't see any. I don't have any problem with it actually from a professional perspective, right? And you can also see that this is a very famous virtual influencer, Makila, have been used at the very beginning. It started to show up on Instagram, and now you can actually they kind of perfect the pipeline of generating like her content, and so you can see a lot of like videos, etc. Throughout social media. And this is probably one of the most famous virtual influencers in this age. It's also like usage for virtual human. You can see for machine learning purpose, like for example, this very nice paper from Microsoft, fake it till you make it. And so basically, once you have the key technology for human image generation, and you can use that to generate a lot of data set, which is really important for machine learning training. So they basically, once they have a way to control different identity, expression, texture, hair, or even cloud, or all other accessories, including lighting as well, then you generate like very many diverse images for your training data. And you can use that for a lot of different applications like facial tracking, facial recognition. All right, so which means that like if you control the technology for generating virtual human images, there's a lot of potential what you can do. You can do like virtual influencer. You can put this character into movie or video games, or you can do machine learning like such that you can train a lot of useful models for everybody to use. So in the early stage, why digital actors matter, or why digital human matters? Like a lot of this technology, they arose from movie industry or video game industry. I think the one thing for movie is that first they want to do storytelling, like they want to tell a very specific story, right? And sometimes maybe you want to bring this person younger or older, or even bring someone from the past and to your current to the current age, or if you want to control or safety. For example, in this film, Iron Man 3, he's jumping off some kind of big rig, and in this explosion, there's no way you want to film this with real person or even with real human. So that's why everything can be. If you have some kind of digital human generation technique, you can use that to complete this shot. And sometimes even the environment is safe, right? Still, like, it's easier to actually employ a CG character than doing some kind of, kind of multiple shot and do some composite. For example, I choose this video feed Logan as example, right? It's basically in this, I think this basically someone also clone Logan, which is Wolverine, and then they want to have two Wolverine kind of interact with each other at the same time. So theoretically, you can shoot this shot with two takes, right? One is we shot from the Hugh Jackman from the back, and the other one he walked down from the stair. Then you can do a lot of composite work to try to make sure these two characters can seamlessly integrate it together. But it'll be much easier if you think of just find a human double actor and just replace his face, so you have less area to paint for a composite purpose, or so that will be much easier. So that's why I was saying, if somehow you can do this, we have some kind of digital human technology, and you can generate very realistic faces. You can just do like a body double and replace his face, and that'll be much easier to complete this job. And one thing for digital human is also very important is mass production, the ability for mass production. Nowadays, you see very successful software like MetaHuman. You can use that to blend different source characters and to create new one. Or I think they even have some kind of tool that allow you to import a facial mesh or facial scan of yours, and using that scan to generate a MetaHuman instead of you playing with the controls. So that kind of hugely facilitate how we can generate digital human. And lastly, there's also like identity privacy issue where Microsoft just scraps some kind of facial recognition data set. So if you have some kind of human generator, like nowadays, this MetaHuman also, I see people using StyleGAN, for example. That's also very powerful way to generate facial images. So which might be able to avoid privacy issue, because you are not like directly retrieve those information from a real person. You are trying to generate face images out of this generator. But everything is about digital human development is starting like very early, from video games or for films. Before they try to shoot the movie Gemini Man, Disney already started to invest this technology back like 20 years ago. But at that time, they made this digital human project, but they kind of figure out, okay, maybe the cost is too high, or the technology is not ready yet. But I'm just trying to play this video and let you know how it all begin with. So like if you want to create a digital human or a double of that real person, right? Basically, you have to do modeling. So they just show using a cast, right? And plus a lot of facial image evidence to understand. Even they try like MRI, for example, just to gather a lot of evidence such that you can build this facial rig. Then you can think of how to drive this rig. You may have some kind of animation source to drive, and also develop shaders to make this face look believable, and add on lighting. Then you can do rendering composite into the final images. So this is actually the source of the film Gemini Man. They did this test, but somehow they couldn't do it at that time. So after maybe almost 18 years, they finally can do it with the help from Weta Digital and do all this digital double work. But they had the ambition to do it 20 years ago. So this was the last shot. They basically try to have these two person interact with each other, which is sort of like what Gemini Man want to do. So for that video, you see there are almost 3 stages for generating a digital human from a more like a traditional perspective. Later on in this talk, I will talk about more about in the recent advances using machine learning to generate face images. But from a traditional perspective, there's always these 3 stages. One is modeling, like if you want to create some kind of virtual human, you want to make sure you know his expressions, particularly if actually your interest is to try to copy a certain actor or actress. And then you have the problem of rigging and animation, how to make this face move realistically. And then lastly is a rendering problem where you want to make sure this digital face looks real, like as presented in a final form. So we can start with the problem of modeling. I think this is probably the one of the most solved problem for digital human, because we have so many achievements over the last decades for tracking and also photogrammetry. So this, I would consider modeling is well solved right now. So you can certainly see this a lot of equipment you can use, and some of them are actually pretty old. Like the cyberware scanner on the left is really like a device from 20 years ago, which is really big and bulky. And now you have handheld solutions for 3D scanning. Also, if you have if you even can just purchase some kind of machine vision cameras with or without the structured light projector, which is fine. But with cameras and also some commercial software like Agisoft, you can successfully just do 3D scanning. And so for the digital human project, though, they actually scan this actor with different expression. This sort of like become a standard for building digital human. When I was at USC at the time, back around 2005, which is like 17 years ago, we started to analyze this problem, how we can get the geometry and the appearance of face at the same time. Because if you remember correctly, like for that Disney digital human video, they actually made a cast of that person, right? Like they make a plaster cast that you had to put on some kind of casting material and remove that and fill in your plaster to make like solid cast. Then they use 3D scanner to scan like the black like a white plaster cast, which there's no textual information. So what we are interested in, can we actually gather shape and texture at the same time? That would be, and also make it more painless. Like we don't want to have some kind of casting material being applied to the face. And with some kind of theory of photometric stereo, like you can actually using this spherical pattern, like lighting pattern, you can see the lighting is a little bit different from shot to shot. Like we apply some kind of spherical harmonic pattern, lighting pattern onto the subject, right? So the lighting has a little bit of variation. This X, Y mean Z means the direction of that spherical harmonics. But anyway, in short, like this is a new approach at that time that we can use these lighting patterns. You can actually derive normal math directly from these images, and plus some kind of strike pattern. This is for photogrammetry that you can similar to a 3D scanner, like you can get a base mesh. So once we have the base mesh and we have normal math, there's a way to integrate those to create a very high resolution of face geometries like this. You can see, you can even this are actually a triangle, like a triangular mesh, and this is not actually not without any like a normal mapping or anything. This is basically there are like medians of triangles there, I assume, because each pixel from your photograph becomes a vertex. That's essentially what the algorithm does. So you can see how all the details can be very faithfully captured, even without all those casing material. And not only that, since you are shooting directly to the subject without any intervention of that casting material, you can get a very believable texture from her. And then we start doing the same thing. Basically, you want to scan this subject into with different expressions, right? And you can certainly see the skin did a lot of interesting things when it get contracted or expanded. Like if it's a neutral pose, then the forehead is really smooth. But somehow, if you apply tension to the forehead, it shows out these little wrinkles, directional wrinkles, which will turn the reflectance here on the forehead become like an anisotropic. So if without any tension, the reflectance is more isotropic, which is non-directional. But once you have these wrinkles here or vertical wrinkles, then the reflectance become very interesting. So that's why I want to get to the detail of all the how skin move along with your expression, because that will change the shading, and the shading will kind of affect our perception. So for example, sometimes you see some kind of virtual human in a video game or film, you don't see them like somehow you don't feel them very real, but you cannot tell why it doesn't feel real. It could be the motion, and it could be the appearance. But I'm just saying we have to pay little attention here, because all these things matters about motion or appearance. So like even the pore structure or the little wrinkle will affect that appearance. So that's why I want to actually faithfully document this. And so you can also see, once you have, like, we actually replace our cameras with much faster high-speed cameras, so we can run this pattern much faster. Then you can start to see we can document pore deformation, and then somehow reconstruct them. Like on the right-hand side, this basically we come up with kind of representation. You can reconstruct those pores. But on the very left, you can see if you just apply a simple bump map or displacement map, the pore doesn't change in shape, right? The pore stays as the same while it's moving. But in reality, everything moves. So and also that will kind of affect the appearance. So this is something like we really want to understand and document. And nowadays, you see a lot of these photogrammetry studios around the world. You can even hire them. I'm pretty sure in some of the universities, they also have this kind of setup, which with advance over the current software like Agisoft or other things, you can actually get a very detailed face model just by using a lot of cameras. So this is not totally impossible to get detailed geometry anymore. That's why I would say like photogrammetry it's pretty much well solved at this point. And then how we can actually use this data to turn that into useful animation rig will be a next challenge to do. So that's what I say. So I think next thing is to do is for rigging and animation, which you want to kind of process these raw scans into like an animation model, and then apply animation to it such that it can move along. So rigging is actually, I will say this in one sentence, just from some kind of raw data, you turn that into an animation representation. And for faces, So this is what it would mean. I think the first process is usually done in the visual effect industry is so-called retopology. And that you basically, if you have some kind of template showing on the right, you want to deform that template to match the raw scan you got from the photogrammetry phase, right? And you can probably sing this famous actor Ian McKellen, which he played Gandalf in the Lord of the Rings movies. So we try to deform this template with some kind of energy. You should try to minimize some kind of deformation energy and do this what we call non-rigid registration. So you deform it and while you fit to this mesh as a target. So once you finish that, and you will have some kind of character look like Gandalf. So that's the first step. And usually the one of the most popular representation for facial rig is so-called blend shapes. Means you have different expression. You can imagine you have a different expression in this blend shape set, right? And when you try to animate them, you need to pick out the right expression, and dial out this weight between them, so you can create different expressions. One way to actually very quickly you can come up with this expression is you can transfer some kind of default deformation into the register model you just got from the last step, right? So here on the top row, I do have some kind of default template which give me some kind of different expression, but it's not the person I scanned. It's just some kind of character I built in the past, right? But still, I can try to transfer this deformation to the mesh I just registered. Then this will give me the plausible expression for that person. And then you can think of that since the registration is kind of free, it's automatic in nature, and also the deformation transfer is also automatic. Then you can actually quickly come up with some kind of like a character which is already ready to use. They can do different poses, open his mouth. It may not be the same expression as a real person does, as we only have the one, at the beginning, we only have this one scan to begin with, right? But through this registration and deformation transfer, you can get a really plausible character, right? And that you can use this for a lot of purposes. Like you can serve as a really high confidence prior in your if you want to do some kind of face fitting or like some kind of facial solver to solve for the expression. And this is already a very good starting point that you can serve as initial guess, or try to use that to regularize your solution. Because I can certainly see, for example, the jaw open or any poses here, they are maybe not from the same person, but it still look plausible. Like it's actually, for example, you want to move the jaw, actually open it up, and the tongue move along with it, for example, and this all looks very believable. And once you have a rigged characters, and you can think of a way to populate them in a more like a mass production fashion. For example, at Activision, we designed this kind of blending framework that given some kind of right now I have 6 different characters. Then there's this bar I can choose like to see, okay, which one I want to have for his face, or for his eye section, or for his mouth. So you can blend different values to create a new face. So we call it like a face mixer. That's when we develop this technology from Weta Digital. So then you can see you can use some. So this method is called facial composite, which is really popular. Like if you certainly use this technology before, if you play like a video game like Xbox or Nintendo Wii, they have this kind of avatar system that you share similar. I think the more like beautiful UI, like you can select different eyes or different head pose, or eyebrow or mouth, for example. But this is the same thing, but except that we can actually generate a whole face and also the expressions with it. So it's a way you can actually mass produce a true facial characters. And the same thing happens with MetaHuman. Basically, you can almost do the same thing, like by blending different people. Then you can change its behavior, or you can do some kind of editing to change, like they have some kind of key point. You can select different blending or choose different color. It's exactly the same thing. So people really want to have this kind of interface to mass produce, right? And for then once you have a rig, then it's the tracking and animation become more important. Like you do want to animate it, or you want to do some tracking such that you can kind of derive animation from that tracking data and to apply that animation to your rig. So at Weta, basically we did some kind of headcan project for the film done on Planet of the Apes. So the actors basically they have motion capture point, the motion capture marker painted on his face, and there's a camera here looking at his facial image, and we use this information to derive animation data to drive this character. Right? And another thing I can show you is this emotion challenge project. So basically, you can see much detail. Like this is the real view here at the bottom. It shows two cameras, head-mounted cameras, and this is one view that you can see the mesh being registered. And we not only solve for the mesh, but also solve for the camera motion, because the boom will sometimes vibrate during the motion. Then you can see how this is the solved geometry, and while solving that geometry is basically also give you this blending weight for that blend shape, so which is sort of like an animation data, and you can apply that to the final final animation rig, and this is what we got from the video. Okay. The eye tracking will be using a different technology because that's not part of the blend shape, but sort of like to give you an idea, like usually what is being done in the movie or video game industry, that you basically they have this head cam, they look at the face. There's usually some kind of marker being applied to the face as well, and use that to actually all the joint information to solve for animation data. Another I see a trend is to employ more cameras to the stage. Like when we have this light stage at Activision, the first thing we did was to do regular face scanning, which is what I presented in the last section. Like you do pose by pose. However, if you can replace some of the cameras with machine vision cameras, and you can actually do some kind of 4D capture, like you captured real time meshes, and you try to register a template to this raw mesh data. So sort of then you can see more deformation in detail. Yeah, this is another example. I want to show what I want to show this is, I think there's one interesting fact. Let me just bring up. Okay, so this is a part where it gets interesting. So you can, she's doing a little bit like try to compress her lip, and then the lip suddenly pop up. You can certainly see from this part because the video is a bit choppy, so I just try to slow down here. But you can see the lip being popped up here, which is like a secondary effect. But if you don't have any kind of setup for dynamic capture, then you cannot get this, because it's sort of like if you just hold your face into a certain expression, you cannot get all the secondary physical effect. So doing this will definitely add up some kind of more, giving your animation data a more believable kind of flavor to it, because you will have a lot of different secondary effect being applied to your animation data. And then you can certainly see if you have the same representation of your animation model, which like all of our character will have the same expression set, then you can easily solve animation data from one character and apply that to the second character, so they will do the same thing. And while we are doing this, so we're also thinking about, like, if we can actually remember, or when I talk about this using deformation transfer and build up like a initial kind of character which look like him, but maybe the expression is a little bit off. So here we can actually, if you can design a mechanism that can actually try to also improve the blend shapes, you can certainly see, for example, in this case, the initial shape, the initial jaw open is not long enough. The jaw didn't open wider enough, so you can see for the 4D tracking, the jaw opens really wide on the real person, but your animation data cannot, animation rig cannot do it. right? So it's caused a lot of error around the jaw area. Also, you can certainly see in the nose also have a lot of error, but that's just because this jaw motion will affect the global head pose estimation. So the whole, because the eye is actually a bit lower in this case, just because the head pose estimation cannot find a really good estimate because the jaw also have the issues. Then gradually you can see we can improve that, right? So you can not only try to solve for the animation data, but you can also inversely solve for the this animation, try to improve the brain shape rig, or try to improve your animation rig such that they can be like you're actually solving not only for the animation but solving for the rig as well. So that will give you a much better fit in the end. And once you have you can imagine once you have a good rig, then you have a better animation as well, or a better head pose, right? So it's all like all these variables are connected. When we solve any animation, you're thinking of like head pose, like the head will move, and also the animation data itself. But the animation data lies in how accurate your rig is. If your rig is not accurate, then you cannot get a very good animation. So they are all connected. That's why we have this pipeline. You can actually solve everything all together. So this is another example where, and initially you can see. Let me stop this video. Like initially you see a lot of error around the cheek area, because I see he's doing some kind of like cheek sock pose, right? You see this dimples here, but the dimple from the template is not deep. It's not deeper enough, right? So once you start to do this registration or improvement over the face rig, it's much more improved. And nowadays we don't even need a big stage. So imagine like it's impossible for everybody to have a live stage with dozens of cameras at home, right? And to give you like really detailed depth 3D reconstruction of face. But sort of like nowadays there's some kind of there are a lot of different mobile, like different a lot of mobile devices already have some kind of scanning capability embedded to it, right? Like iPhone, they have this Face ID sensor, which essentially is a laser scanner. As you see on the screen, it projects some kind of infrared laser pattern to your face and try to estimate your face shape, right? And basically they use that to do you can use that so Apple have this memoji function where it's not only like this Face ID for unlocking your iPhone, but also sensor for like animation purpose, right? So essentially your this little device iPhone becomes this like become like a simplified version of the light state, which can do like depth scanning of your face and try to understand or what expression you are doing, which is essentially what we did. The algorithm is actually very similar. It's just it's a matter of a different kind of input. So here the input is a single camera with some kind of there's also RGB camera here and with some kind of depth information. But all this algorithm, they basically try to have some kind of model to register to this data, right? While employing some kind of regularization, for example, making sure the animation is smooth, or making sure it actually can the deformed face can reach to the depth image or the 3D scan. And you can certainly see that people are being really clever or creative in this case. That, for example, some of this like I would say low budget visual effect studio, they already try to employ a lot of the AR kit. Like this person, he tried to put a iPhone on his head, right? And also this also in front of him, his face is actually a mirror, right? So I demonstrate you can put some kind of machine vision cameras from our Activision project, right? But but those cameras tend to be very expensive. Also, you might maybe want to put two, so you can get a stereo sensing for two cameras, right? But now you can just put an iPhone, right? And you don't even need to write a solver. You probably just because the AR kit already solved this facial expression for you. So this is this is kind of like an all-in-one solution. All you need to do, I see some people actually mount iPhone in front of their face, but iPhones tend to be very heavy. So this is a clever kind of way. Actually, you put a mirror here. Mirror is very lightweight, and try to reflect the facial image to this. And you can see this a little device. I think it's a half mirror, which is very similar to what you have in your DSLR camera. So that will kind of reflect your facial image to the iPhone camera. So the iPhone can solve for the AR can solve for the facial expression. But I guess in this sense, you lose that depth, right? Because the depth camera will not function very well because it's not actually looking at. Actually, I don't really know, but I assume the depth it will not work very well in this case. But iPhone, you can solve for facial animation even with your RGB video feed, which is fine. I'm just trying to make a point where you can nowadays you can use a lot of available commercial tools to facilitate visual effect production. So like us, we at ByteDance, TikTok, so I'm involved with some kind of building something very similar to Apple. But so if you want to use AR key, you can only use on iOS devices, but not on Android devices. And there's no solution actually for Android to do facial animation. Like there's no solution for Google. As I said, maybe there's a third-party one. But from Google's AR SDK, which is AR Core, there's no facial animation capability there. So we have to actually develop our own. Then we can serve both Android and iOS, right? And you can see people are using this to be very creative. Actually, this is a person. I don't know whether she's a male or female, but she's playing different parts, right? Like she's actually one person, but playing different people, different virtual characters, and try to make a video out of it, right? And so this has become very creative, where you can imagine, because this is essentially a virtual production. Like it kind of separate your performance with your presentation. Like your presentation can be in many different forms. Like one person can play different parts. The first thing I saw this was from the movie Polar Express, where Tom Hanks played the little boy and also the conductor in that film. But this is so in this sense, you can the mobile device become like a virtual production tool, right? It's basically serve as capturing some kind of movement or animation from this actor. But how do you want to present this motion? It can be different form. You can choose different people, right? So I think that's it's very interesting to see, right? I think this video, I think he used like 4 people to do, so which is really interesting. And while I couldn't say much about what we did, but I think this paper from Roblox from last year's SIGGRAPH talk, I think share very similar architecture than from us. Like it's basically involves some kind of training data, like you have label data with landmarks, and also some kind of expression you have to prepare in advance. Like this fax weight, you can basically think about this as a plane shape weight, right? So you have to prepare this training data, and the regression model is very similar as a convolutional neural network. So you can see here this what it's called like multi-text. By means multi-text means you have multiple losses. Like one is landmark loss, and the other one is the plane shape loss, right? And then once you have enough training data, you can certainly train the model with like more like a supervised learning way to train this thing, and it works pretty well in that sense. And not only that, you can certainly see since this is the neural network, basically just take your video feed and generate animation data. You can apply to anything, including MetaHuman. So a lot of this new technology being developed for the consumer product it gradually can be applied to visual effect or video games, and the boundary of high-end visual effect or video game or even consumer graphics is getting very diminished. Right? Okay, so this will cover my last part, which is rendering. So you can always you certainly know this actor, Mr. Beam. So it's a photograph of him. But what is this? This is look like a photograph, but you can certainly see it's not that. It's real, but it's not that realistic. So it turns out a lot of people, for example, on the art side, like on ArtStation website, they're actually very interested in building this 3D poetry, right? They look basically they will find like a poetry view of a real person and start to make a 3D model of it in the same camera view, and try to sculpt it and adding textures and finally render it, right? So you can still see that it's two images. I can tell. Okay, if the left one is real, right one is okay, but not so great. But if you only look at the right one, let's just say if I present to you this one in the first place, I would say some people actually depend on how far you see it. Right? I would say not many people will kind of know. Okay, this is fake, right? So I think we are at a level where it's close, but we still have a little bit this so-called like uncanny valley thing needs to be solved. For some reason, I cannot tell. I always feel in this fake image or the CGI image, the tie, the necktie is really it's really good. It's really realistic, right? I think the best part is actually the necktie. To me, the shading looks very realistic, but the face is kind of off. I think the problem with the hair as well is it is too homogeneous. Right? The real hair is more messy. Right? But it really depends on how much effort you are putting, because for example in the movie Gemini Man, I think it actually can be rendered very realistic, but it just depends on how much budget you want to put into fine-tune those parameters. For example, like subsurface scattering is always very difficult for skin rendering, and it needs a lot of tuning, because we tend to have different structure underneath the skin, and it will definitely affect how light being scattered throughout the face. So while we are ICT, we tend to use another different approach that we actually capture real data. So you can imagine instead of trying to simulate, we simply just capture a huge amount of data of how light will interact with skin. For example, this is a maquette for the movie, The Curious Case of Benjamin Button, right? So if you can actually capture lightings from different angles, then you can actually have a way to reconstruct the final images under different lighting conditions. Like this is maybe under some kind of reddish illumination or like a yellowish illumination. But sort of once you know how why did I give you this lighting direction, what the image looks like, then you can actually reconstruct everything you need. So that's why I think the visual effect team from Benjamin Button did a very good job on getting those data and use that to calibrate their shaders. So this is still using shader to render. You can see the different layers, but they have a better way to calibrate this with the real captured data. So that's why when they are applied to the final shot, it looks really believable, right? Even though this is already 14 years ago. but still, this looks very good to me. I don't see any part that make me feel this is like on nature, right? So this pass actually for me it passes the uncanny valley part. So same thing being applied. So you can see same technology being applied. So instead of like try to analytically try to decide what the shader parameter will be, I think nowadays people just try to capture new data and try to run through some kind of optimization to gather good shader parameters so to be deployed into their film. And lastly, I want to say something about the general element, which they actually took a slightly different approach, that they actually come up with some kind of simulation for skin details. You can certainly see they have like some kind of artist drawn contour, flow contour, and then use that as a guide to generate all different kind of skin details. And it actually looks very believable. And this is actually, it's all synthesized. It's not data driven. It's basically someone have some idea to synthesize this thing and product that. And I think it looks very good. So because this kind of resolution is already at a level where maybe we cannot capture, or it can be very hard to capture. Somehow we might need to some kind of kind of formula you can actually generate those details. But the solution they choose actually is very I would say it's very good, and the result being very believable. So when they do this, when I watch this Gemini Man film, I don't actually have problem with their final digital phase. I do have problem with their other visual effect element, such like the simulation of the motorbike is not very good to me. But I don't have problem with the digital phase there. If you haven't watched it, I encourage you to watch it again, just to understand how good the digital phase can be. Yeah, it's about getting at the last part of my talk. I will try to say something about deepfake. So you can probably see deepfake being very popular these days. Like this one of the creator on TikTok is Unreal Keanu. He did a lot of deepfake on him. You probably also seen the deepfake Tom Cruise as well. So they do a lot of funny videos, and using celebrities' face. And if you have any interest in deepfake, you can certainly go to this link, deepfakelab.theglassroom.org. It's mostly tell you how deepfake is generated. Yeah, but I think the interesting I've found for deepfake is this part, where okay, sorry, go back. Yeah, this part where we see a lot of new deepfake technology being published or invented over the last few years. But then I think one issue here is they all use the very old landmark detection to start with. So imagine like we are building a lot of very high end race cars, but the engine itself is actually very old. And one of the very key components for deepfake is, like, you can still see they're using this multi-pi landmark, and maybe the detection can be very depend on how you. Some people have trained, but if you use the original multi-pi, it's actually not very good, or it doesn't have a lot of the details on its lemma set as well. I would say you may want to increase the lemma to like 100 to even 200, such that you can get all the details. And the landmark itself is actually only key point. So, and all of this is because this new technology being running on kind of older landmark model, and I think it's kind of like a limit how much like quality is actually the deepfake can produce. So this is one of the challenges there. Unless some people actually try to improve this, like I see, for example, Microsoft this fake it till make it paper. They use synthetic data to give you a much broader coverage for the lemma. I think that's a very good sign. Like people start to look at this. Yeah. And you'll certainly see style gun being very popular. This is probably like using the scan model, you can generate like an embedding where it covers an entire human like images, which is really powerful. Like we use this also for I'll cover it later, generating kind of training data out of nowhere. But some people use this, for example, they can kind of manipulate the style gun different layers, so creating some kind of cartoonish effect. I think in this way, in this tool, Tonify, they simply changed retrain kind of refine the top layer of the style gun, so you can have some kind of geometric change, bigger geometric change, while keep the final layers the same. The final layer will basically give you all the realism details. So once you have that, you can see people being transferred into more like a cartoonish kind of style. And you can certainly see some advance on learning motions from one video and apply that to another input images, right? And you can certainly apply all different kind of approaches to generate really interesting results. Like for example, you can see this animation characters being generated by some kind of Tonify, then being driven by this first order motion technique. So here, whatever showing on the right, there's no 3D model, there's no anything like animation data. It's basically feeding some kind of information being retrieved like intrinsically from the input video and be applied this to the right. And there's no rendering framework, there's no lighting, you don't need to compute like the shading parameters. So it's basically just a neural rendering framework. So which is like very interesting. And we had a paper as well just to try to do stylization, which is very similar to Tonify, but just try to manipulate style guns such that given some kind of examples, you can build out different style of the original input image. This is being very popular for the social media such as Snapchat or TikTok, where you can apply like a filter and sort of creating new content based on it. Okay, so this I mentioned earlier. The style gun also being very powerful, like it can generate facial image from nowhere. Like for example, so we had a paper where we want to make our model to generate in more diverse scenarios, right? So a lot of the training data we capture, there's no facial hair or there's very little with eyewears. So we want to kind of hallucinate those images. So you can certainly see on the top row, very top, there's input images, but we can add facial hairs or adding eyewears while keeping the same expression. So you can manipulate style gun such that you can actually generate those images. So I actually see, to summarize, I actually see two different approaches right now, and I think they are actually related to each other, but right on the left-hand side is more like a deepfake. It's used for facial replacement or directly like neural image rendering. I also see some people actually try to use like a nerve to start to use nerve to kind of encode facial performance, or like Facebook, they have kind of codec avatar where they encode like facial geometry and texture with autoencoders. It's sort of like a lot of way to use neural rendering to generate face images, right? And you really need a lot of images and video that to make it right, because it really depends on like where this original footage being shot right now. If you don't have this similar lighting condition, then it might actually not work very well. And also this deepfake usually being constrained to the body actor. So you have to find someone that you look really like Tom Cruise. Like I think this person on the left it's already pretty much look like Tom Cruise. You can certainly see the eye layout, like the proportion of the eye on mouse is very similar. That's why he can add up to the success of the the final output. Then we can also see another trend, which is just procedural face generators, like using traditional asset. Then we can do a lot of measurement, like facial scanning, skin reflectance measurement, and all that kind of thing to make it more believable. However, all those procedures are not perfect yet. Like particularly for skin rendering, I think we still need to have a lot of work to do to make sure skin is can be rendered in a very believable way. And I think actually these two kind of affect a lot. For example, if you have a much better procedural face generators, then you can use that to generate a lot of training data to help your deepfake. So it's actually very relevant to each other as well. I think the final goal, the final holy grail, is actually to actually physically understand how we can actually by means physically means we have the right formula to render faces or to understand how face move, which means right now I think some kind of simulation based face rig can be very popular these days, because we start to try to understand using all the computation power we can have, right? Because using machine learning, you might not actually try to understand how it works, but you can certainly lay out some kind of embedding from the data itself, but it's still very not like trivial to understand how things works. So when I see this the demo for the Matrix Awaken, this is a promotion for the Matrix film from last year. It actually looks very believable to me. I think they did a very good job. And these are actually rendered in real time, and I don't have any issue. I don't have much issue with these images. Right? So it's certainly, if it's possible, consider the trend of how face being rendered using traditional pipeline. I think at least the prediction is linear. We see some kind of a huge jump for deepfake. Like you can easily go to the different quality level by using deepfake, but somehow I think right now the quality being stuck there. You hardly find any new improvement, but the improvement over traditional pipeline is incremental. Like you can certainly see from year to year, different year, the quality of this rendered face rendered face being very believable. Okay, so yeah, 2 minutes, sorry. And then we go continue. So I introduced these 3 things, and they are new way to do these 3 steps. And also we cover a little bit about machine learning. For future work, I think okay, I want to say a little bit more about future work. So I think one thing is how you can control the embedding, like how you can. So for machine learning, it's all about embedding. You extract embeddings, but embeddings are not really friendly to control. Like I'm showing my own MBDS embedding of my own facial data set. Like I process all my videos of all possible facial expressions, and this is embedding, right? But how can you develop some kind of fast control or local control with embedding? So or map to this embedding. I think it's not that trivial. And secondly, I certainly see, I mentioned earlier, mobile device can be used for production use. So for the TikTok avatar application, we only replace the face, but you can certainly imagine your CG, the background can be also CG, and the body can be also CG if you have some kind of body tracking. Then your mobile device or your camera is merely like a motion capture device plus some kind of virtual camera, and all of this the rendered content can be CG. And I think that will open up a very interesting application. Even you can imagine it's like a shooting in the metaverse, shooting movies in the metaverse. And this is also, I mentioned earlier, the rendering is not perfect yet. We want to try to improve all the procedures to understand better about how face moves and how skin reflect light, right? Such that we can actually do the simulation correctly to pass that uncanny valley. and also very important for the ML is basically once you, so if you look at their images, it's not, I won't say it's very realistic, to be honest, right? But certainly maybe the machine learning algorithm doesn't need to be, be super realistic. So, but as long as you can reduce that domain gap, right? You want to make sure your image can be realistic as possible, and certainly you can improve the throughput of your machine learning algorithm. So I think still this is very relevant, right? And lastly, I see a lot of interesting things on internet, particularly this year. There's so many interesting machine learning things coming out, including like just in the last few days, like people talking about the chatbot for Microsoft OpenAI. So I see a lot of interesting use for using machine learning with traditional pipeline or not to generate new contents. Like this case, like basically render like MetaHuman using a kind of neuron implementation, so making like a stylized rendering of her. This is really interesting to me. And I see a lot of this use on Twitter or social media. People try to bring out different machine learning technology together to generate interesting content. I definitely see this is a good way to go, and definitely want to learn more about this as well. Okay, and this summarized my talk. And thank you for your patience. I sorry I passed a little bit time, but I'm available throughout the next half hour or so. So thank you for participation, and please ask me any question if you can. Thank you.
Thank you so much, Alex.